All right, let's go ahead and take a look here after doing this warm-up, right? Like I said, you've already tested these points last week, right? You figured out when it's increasing, right? When is f of x, when is f prime of x, I'm sorry, when is f prime of x positive, right, or greater than 0? And you also found out when f prime of x was less than 0. And you also found out when it's equal to 0 by finding these critical points up here, right? So you found out when it's positive, when it's negative, to tell me when it's increasing, decreasing. And you guys also found out when the second derivative is positive and when the second derivative is negative. I'm hoping you guys are okay with my notation here, this greater than 0, less than 0, right? It's just a way of saying like f double prime is positive. It's just the notation for it, right? Positive, and then this one right here, f double prime is negative, right? So with that being said, I'm just taking what we did last week and putting it into a table, right? Now, you'll say, why? Not me. And I agree. I don't really understand why either, but it's just a way of organizing your data. So if you were ever asked to graph f of x based off of the derivative and the second derivative values, this will help you, okay? So knowing these sign chart values, you know when is a function decreasing, when is a function increasing, and you also know its concavity on those intervals, right? So this right here is going to be decreasing, right? Decreasing and concave down. Concave down. There's got to be a, we got to find a way to shorthand this. I don't want to write this the whole way through. Maybe for decreasing, we'll just write dec, and then for concave down, we're going to write concave down. Maybe just start abbreviating everything, right? Or we could do like Calvin, is draw notations here. This is increasing, so it's increasing like that. And since it's positive, that's a concave up. Right over here, this is still increasing, and this time it's concave down. And this one, it's decreasing, and then it's concave down as well. I like that. I like that. Actually, that may be a little bit easier than writing out the whole word. So the original function f of x, right, looks like this. It's the negative x to the fourth plus 18x squared. Okay? Now we have this information right here, which is going to help me to graph it, right? And that's what I'm going to do right now. I'm going to go ahead and graph this guy. And you guys can do this in your notes as well, just to practice along with me here. I'm going to go ahead and draw some shapes here. I'm going to go with this nice little cheater here, XY value, like so, and maybe make it out that wide. Okay? All right. So graphing this guy out, I know that from negative infinity up to 3, the function is increasing and concave down, and then it changes to decreasing concave down at 3. So I'm going to make these marks out here. So we got 1, 2, 3, and let's do it in the other direction. 1, 2, 3. I'm not going to mark, I could mark the y's, but I don't know what these values are. Right? I'm not going to draw this to scale. I don't know how high up it goes or how low down it goes, right? But I do know at 3, it's going to change from increasing to decreasing. And I'm just going to mark it, let's say, oh, I don't know. Let's just make a pretend mark that f of 3 is somewhere right here. I don't actually know if it's right there or not. Right? But I'm just going to mark it just to mark it. Okay? Yeah. So I'm saying the function is doing this. It's increasing all the way up to there. And then at 3, it starts to decrease. So I'm going to draw it like that. And I also know that it's concave down all the way up to the square root of 3. Okay? All the way up to the square root of 3. And where's the square root of 3 at? Does anybody know what's the approximate value of the square root of 3? Anyone have a approximate value for the square root of 3? Anyone know it off the top of their head? I'm gonna have to go plug this in the calculator. I'll go plug in the calculator. 1.7. Thank you. Oh, thank you guys. Thank you. 1.7. So negative 1.7 is roughly around here somewhere, right? So somewhere at that point, I need to have it change from concave down, which is what it's clearly doing right here, right? It's concave down from here to here and concave down from here to here. But that at some point, I need to change it to concave up like that, right? And I'm going to take into account a lot of things to factor that in. It's still going to be decreasing all the way up to 0. So at 0, it's going to change. So I'm going to make 0 like, I don't know, let's make it like right there. I don't actually know if this is where it's supposed to be. I'm just marking it there for now, okay? So I know that at 0, it needs to change from decreasing, right, to increasing. So it's going to do something like that. And I also know that it's going to be concave. Oh, whoa, I messed up on this one. This was supposed to be concave up. right? It's supposed to be concave up on this interval all the way up until about 1.7. So it's supposed to be concave up like this, right? All the way up until about here. So that right there is supposed to be my point of inflection. Now, when you're drawing these, you're going to struggle to draw those points of inflections exactly where they are, and a lot of things, and a lot of people always do. So don't stress out about making that point perfect. It might be down here, it might be up here. Just try to make it look like, hey, around the critical points, you see where it's concave down and where it's concave up very clearly. Okay, if you have a point of inflection there, don't focus too much on it. Just kind of get the idea of it. Okay, and then it's going to be increasing, and again, it's going to change from concave up to concave down somewhere at 1.7, which is over here, right? So it's going to change, and then at 3, right, I'm going to again have to change from increasing to decreasing, so it's going to look something like that. And there is my rough sketch of what this function might look like. Now, how high does this go and how low does this go? We would have to actually just evaluate those points, but we'll focus on that later. To just get the idea that you can actually sketch these things just based off of the first derivative and the second derivative, right? That's all you really need. And of course, you'll say, Nakmi, why even do all of this when we can just go on to Desmos? And I'll say, yeah, that's true. You could just go on to Desmos because we do have a function here that is easy to calculate and to graph on based off the function that's given to you. But of course, you guys know on the AP exam, they're not going to give you a nice polynomial. They're going to give you a chart of a piecewise function, and you're going to have to be able to sketch it piece by piece based off of what they give you. Anyways, let me show you here. You'll say, Nami, that looks nothing like what you sketched. And I'll say, hold on a second. Just let me hit it to a nice value so we can actually see what's going on here, right? So we got something like that, and this is going to go all the way up to, what was the highest point on there? Oh, there it is. So there we go. So it looks like that, right? It looks like that. So the highest point that it reaches at is still at -3 and at 3. Those are your local maximums, right? And I just didn't know that the height goes up to 81. So I can just go in there and just be like, oh, it goes up to 81? Not a problem. Look, I just happen to draw my marks right here, which happens to be at 81. Yeah, not bad, right? And you'll say, Nakmi, what about this line right here? And I was like, oh, well, I can just go in here and just go in here and just just pretend that line never really existed. And some people will say that's cheating, Nakmi, and I'll say, no, it's not. I'm just editing my graph. That's all. Editing my graph just so it looks correct. Going through all the way like that, there, and there. All right. And then I'll just say, oh, originally the axis was right down here at 0. Haha. And there you go. Right? So we have it like so. So 1, 2, 3. 1, 2, 3. There's our graph. I know it looks kind of janky, but I'm telling you right now, the idea is this, right? Knowing when a function's increasing, when a function's decreasing based off its derivatives and its concavity, you don't need the original function. You can actually sketch a graph based off of those informations alone. And you're going to actually need to know how to do that. So you're going to have to go backwards and forwards. Sometimes they'll give you a graph, and you need to identify when is the function increasing, when the function is decreasing based off of the graph. So you don't even have the function. You have to look at a graph and say, oh, the first derivative is positive from here to here. The second derivative is positive from here to here, right? Based off of things like that. Let me show you a problem like that. So anyways, before I do that, though, are you guys okay with how we got the signs for this table? And I'm gonna pause there for a second. Let me know if you have a question. Now's the time to ask, and I can answer them. Right? Any questions about how these signs were received, or how you guys got these signs, or how to get the increasing, decreasing information? No one's answering or anything, and so I'm going to go ahead and move on. And then any questions on how I applied that information to make this sketch of this graph? How do you get increasing and decreasing again? Okay, so to get increasing, decreasing, all you have to do is go to the first derivative, right? And then plug in values. Oh, yeah. Okay, so I guess I should say the first thing you need to find is the critical points, right? So what you're doing essentially when you take the first derivative and you set it equal to 0, you're finding out when does the derivative possibly change signs. So these guys right here are our critical points. So with those critical points, right, which is going to be at -3, 0, and +3, it creates intervals for you, right, Calvin? So it creates these intervals. So it creates this interval from here all the way up to 3, and then from -3 all the way up to 0, and then from 0 all the way up to 3, and then from 3 all the way to infinity, right? So those intervals, you need to test in the first derivative to see if it is positive or negative or not. So visually, you can see this is positive, but how we would have tested this if we don't have the graph is we'd pick a number from -infinity all the way up to -3, plug it into our derivative, and see that it comes out to be a positive number, right? See that it comes out to be more than 0, right? And then that happens over here as well. So if you test that over here, you would be testing a number from -3 to 0, right? And again, you test it into the first derivative. So like, for example, I'd pick like, I don't know, -2, and I see that that comes out to be a negative value, right? Yeah, so that's how we did that, Calvin. So that's the idea. And then I'm hoping you can see it, right? Increasing, decreasing, increasing, decreasing, and it happens to work exactly where our intervals are for our critical points. And that's always going to be the case. That's why we find those critical points. So hopefully that helped out. And thank you, Calvin, for asking. I really do appreciate it when you guys ask these questions. Because honestly, if you never ask questions, I'm just going to assume that you guys get it all. And then, which is not a bad assumption because you guys are smart, but I can't help you if you guys don't let me know that you need help. All right. What was I doing? Okay. So for example, I wanted to show you things like this. All right. You'll say, Nakmi, I could just plug the function into a Desmos and it'll graph it for me. And I can see when is it increasing, when it's decreasing. And that's actually one of the things you do need to do. You need to be able to look at a graph, right? Not based off of the function, and tell me where is it increasing, where is it decreasing, where is the concave up, and where is the concave down. So we are going to practice that right now. So I'm going to go ahead and put this up on the screen real quick, just so you guys can see right here. Let's take a look at this problem. Can you guys see this problem okay? All right. If not, I'm going to screenshot this and put it onto the other screen. But see here, it's asking us, right? This is the graph of the derivative. This is not the graph of the function. This is the graph of the derivative of a function. So this is a graph of f prime. It's not a graph of f. It's the graph of the derivative. Determine all intervals on which the second derivative is greater than 0. So remember, when we used to think about, hey, second derivative tells us where the first derivative is concave up or concave down. But remember, this is not a graph of the first derivative. This is a graph of this. I'm sorry, this is not a graph of the first function, I should say, the original function. It's a graph of the first derivative, right? So when you're looking at the second derivative, you're technically looking at a derivative of a derivative, right? And you say, what? Knock me? What? So check this out. I just need to check this out real quick, right? For this particular answer here, I'm not going to be looking at where it's concave up. That's only true if you're looking at the original function, but we're looking at a graph of the derivative. So if this was not f prime, if this was just f, I would be able to tell the person, hey, the second derivative is clearly concave up and positive right here from -9 to about like -4. But that's not the case, right? This is telling us that this is f prime. So this is a graph of the derivative. The second derivative is positive wherever the first derivative is increasing, okay? So the first derivative is increasing from -5 all the way up to about 2. You see that? It's increasing because it's going up those values from -5 up to 2. And that's all I would put down here, right? For that notation. So let's see here. Actually, it's actually not increasing there. I think it's 0 at -3. So you got to be careful with this, okay? So I'd say the function is increasing, right, from -5 all the way up to -3. And, right, it's also increasing from -3 all the way up to 2. Now, why don't I include -3 as part of where it's increasing, even though you can kind of see it's on that interval? But I'm believing at -3, we have the derivative is going to be equal to 0. Now, I could be wrong because my eyes could just be playing tricks on me right there. But I'm just going to go ahead and go with it. This is a bad example. I should have picked another one. But that's right there. See here, all we got to do here is mark that it's increasing from here to here. Well, it looks like they would have accepted that. Oh, yeah, it looks like they would have accepted it from -5 to 2. So they would have taken that point. But anyways, right? We got to be able to, like I said, like I know you guys are like, we can just plug in the original function into Desmos, but I'm telling you, you're going to get problems where they don't give you a nice polynomial function. They're just going to give you a line that is a function, but we don't have the algebraic representation for it, right? We don't have the algebraic representation for it. So let's go ahead and let me show you a new problem here. Are all these just derivatives? Oh, none of them actually ask for the first function. That's not good. Hold on a second. Oh, that's analyzing the derivative of the graph. Well, duh. I mean, of course, that's not going to have the original function. Okay, so let's take a look here. All right, let's take a look here. So I don't really care too much for this part where you compare which one's greater than which, but I do care about being able to determine when. I guess I do care about those values, but I don't really care about the way they ask this question. Anyways, I'm sorry, I'm letting my own personal preference or opinions talk about this. Anyways, the twice differentiable function is shown below in the domain from -9 to 9. So here's a function, f of x, right? And they say it's twice differentiable. It just means that you can take the derivative of it twice. The derivative of it twice exists. So the first derivative exists and the second derivative exists, right? They also tell us some important factors, that we have a point of inflection at -4.7. So these green dots right here, and -0.5 and at 4.2, these green dots represents point of inflections, right? Which means the second derivative is equal to 0 only at those points. The second derivative is equal to 0 only at those points. Or I should say concavity changes only at those points on this interval. Okay, shown by this right there. Determine what can be said about the values of f of 1, f prime of 1, and f double prime of 1. So let's go ahead and take a look at this graph right here. So I'm going to be looking at it from here. And remember, the green dots are where you have it, where you have your points of inflection, meaning they change from concave up to concave down only at those green dots. So let's go ahead and take a look here. All right, let's go ahead and let's make that a little bit bigger so we can take a look. So 1 is right here, right? 1 is right here, okay? So f of 1, what can you guys tell me about f of 1? Don't overthink this. What is f of 1? Just by looking at this graph. Can you guys see it? What is f of 1 equal to? Local max. Yeah, that's true. That's true. It is a local max. And it has a output value of 2. Very good, Brian. Very good. Has an output value of 2, and Monica's saying that it looks like it's a local max. And if I zoom in there, it kind of does. It kind of looks like it's increasing, changing to decreasing at that point, doesn't it? What does that mean then about the derivative at 1? If I have a local max there, if it's changing from increasing to decreasing, what does the derivative have to equal to at x equals to 1? And I hope you guys can see that the derivative is going to equal to 0. Right there. Can you guys see it? Does that make sense? Why is this equal to 0? Because it's like a little mountain, right? It's kind of like these guys right here. They're going to equal to 0 around these particular points as well, because they're critical points, right? And you need to be able to see that. And that's what I'm trying to say. Some of you guys are able to see it based off of this one, and that's awesome, right? So the derivative is going to be equal to 0 at that point. Now, here comes the hard question. What can you guys tell me about the second derivative at that point? What can you guys tell me about the second derivative? Don't think of a numerical value. You won't be able to tell me the exact value of the second derivative there, but you will be able to tell me something about its sign, right? Look at 1. And remember, what does second derivative tell you? Second derivative is looking at the concavity, right? And look at 1. What's the concavity look like at x equals to 1? Positive, negative. Well, before we go with the positive or negative, right? Tell me the concavity about it. What do you notice about the concavity at 1? What's it doing? Concave what? Concave down. That's right. So at x equals to 1, we have something that's concave down. I already wrote concave. Not me. Why are you writing that twice? It's concave down. And that's why both Brian's and now Monica is saying that it is negative, because when you have something that's concave down, that means the second derivative, right, is negative. Second derivative is negative. And that's it. By the way, I shouldn't care too much about this problem, but so what this thing is asking right here is for you to compare these values. So what's the smallest value, what's the largest value, and what's in between. So if I know that f double prime is negative, this is probably the smallest value. If the function is 2 and this one is 0, then I know that this is the largest value. So it goes smallest, second, and one in between, and then that's the largest. So the answer that I have for this one is going to be f double prime to f prime to f. So it'll be this guy right here, like that. I don't really care too much about this, but it is an important factor to look at. So yeah, that's that right there. Okay. So let's go ahead and I'm going to give you guys one problem to try on here. I'm going to put it on Delta Math right now. So if you guys could sign into your Delta Math, this is not this is just a in class, just for you guys to practice. You guys are going to all have different problems. Let's see how you guys do real quick here. So I want to go ahead and have you guys test this real quick. We'll do that right there. And I only want one problem, right or wrong, just try it. We'll go with that. In class practice. Right, in class practice. For you guys right here for period 3, when is this going to be posted? Right now, when is this going to be due? This will be due at the end of class. So this is going to go all the way up to 10:37. Doesn't really matter because you guys are just going to do it right now anyways. So let's go ahead and try that. So I've opened it up. Can you guys go on to Delta Math real quick and try one problem of this? Of this determining signs, and see if you guys are okay with it. See if you guys can figure it out. It's multiple choice, so you just have to pick which one's greater than which. But I think what's more important is looking at these problems and calculating when is it increasing, when is it decreasing, right? When is it concave up, when is it concave down? All right, so here's a new problem for me, right? And if you guys are still stuck, you can watch me to do it. If you guys get it, you can work on it yourself. But see right here. Right, from -9 to 9, they want us to talk about f of 2. So 2 is right there. And 2 also happens to be where the point of inflection is. So for me, my point of inflection tells me that at x equals 2, the second derivative is actually going to equal to 0 there. So that's not bad. Go ahead and let me copy this real quick. And then I'm going to take a look to see how you guys did on your answers here. And I won't put you on blast if you got it right or wrong. So please don't fret. Don't worry if you get it right or wrong. But try it until you get it right. It would be nice. So let's take a look here at this problem right here. All right, we need to look at f of 2, f prime of 2, and f double prime of 2. All right. So we have here f of 2. I hope you guys can see it. Oh, that's interesting. F of 2 for me here is going to be 0 because the function value is equal to 0. Right? And f prime of 2, that's going to be a positive number. Right? F prime of 2 is going to be positive because it's clearly increasing. So I can say that this is positive right there. And f double prime of 2, they're telling me that's a point of inflection. That means that that's also equal to 0. Right, just by looking at that point, that's the piece of information I'm able to gather here. How did I answer that if those things are the same? Oh, they have me just enter the value. Oh, how did that compare? Oh, I'm an idiot. I should look at these things before I freak out. So they're telling me that f of 2 is 0. I can just, oh, hello. So remember, less than 0 means this is negative. Greater than 0 means it's positive. So the first derivative is increasing for my function right here. And the second derivative is 0 for this one right here. Oh, I'm sorry. I was being silly there. But yeah, there we go. Go ahead and mark that out. And I got myself a check mark there. What's this little X sign down here? Anyways, so that's that one right there. Let's take a look at how you guys are doing. I'm not going to put you guys on blast. So let me go ahead and move this over to the side right here so you guys can see that right there. Or you guys can see it. I can see it without you guys seeing it. I'm gonna put it on my other screen over here so I can see how you guys are doing for this in-class practice. It looks like not many of you guys are trying this. What's going on here? Why do I only have? Oh, wait, a couple of you guys have it open. Okay, good. Okay, I was like, about to get angry. But yeah, good. A couple of you guys have it open on Delta Math, and you, oh, good. You know what? This is my opportunity to give you more points. So I'm gonna go ahead and take a look and refresh and see who has the check mark right now, or attempted it. Let me go in there. Let me get you your points. You're over here. Let me go ahead and bring this over here. So these are the names I see who have opened it, right? And they're currently attempting a problem. So I'll give you some more time to work on that. It should take you about a couple minutes anyways. So I see you guys who have opened up Delta Math to attempt this. So these are the names I see so far. So I see Sydney, Eric, Alejandra. Do I see you in there? Alejandra, I don't even see you. Oh, you're not even. Are you even here? You're not. I don't even see you in my Delta Math. Let's see here. David, Diane, Emily, Julia, Calvin, Jocelyn, Shirley, Grace, Max, Joe, Angela, Areli, Monica, Sam, Leslie, Jeffrey, Diana, Fatima, and Brian. These are the ones I've seen in there. Thank you for owning up and trying and attempting these. All right. Ava, you think you're there as well? Did I not mark you, Ava? I thought I did. Oh, Ava, I don't see you in there. Let me refresh it. Ava, you are in there. There you go. Thank you for typing that out. Anyone else want to let me know that I missed them? Ava. Brian N., you are in there as well? Okay. Brian N., I see you in there, Brian. I see you. What the heck? Why didn't it mark you earlier? Cheyenne, you're in there? Cheyenne, I thought I got you. Did I not get you? I think I might have gave you the points already. I think. Leslie R. Same thing for you, Leslie. I think I got you. Did I not? Whatever. Let's just mark you in there. All right, there we go. Okay, there we go. Let's go with that, and let's take a look. So let's take a look here and take a look at some of these problems, okay? So you guys will have this open. You guys can try this out. It's just for you to practice, right? But I do want to compare this, and I do want to check these values here. So let's take a look at this one right here. So they're asking us to focus on f of 0. All right, so I'm going to take this graph right here, and I'm going to put this onto the screen. So if you guys could just wrap up which one you guys are trying, and let's take a look at these ones as a class real quick here. So let's take a look at this guy right here. Right, this one was asking us to take a look at f of 0, f prime of 0, and f double prime of 0. Right, so they tell us that, remember, the green dots, there are points of inflection. So I have a green dot right at x equals to 0, which means the second derivative at x equals to 0 should equal to 0, because it's a point of inflection, right? They tell us that green dot means a point of inflection, means that it's going to be changing from concave up to concave down. Okay? Second thing, what can you guys tell me about the function itself right there? The function value itself at x equals 0. Can you guys see that it's going to equal to 2 right there, right? It's going to equal to 2. Are you guys all right? Yeah, Monica, that's right. It is equal to 2. Now, here's the tough part. What's the derivative equal to at that point? What's the derivative equal to? Because right here it's increasing. Right here it's also increasing. But at x equals to 0, I hope you guys can see it. The tangent line right there looks almost flat, right? If you zoom in, right, it looks almost flat right there at x equals to 2. If I were a betting man, I would say that the derivative right there is also equal to 0. Is that okay? That's the markings right there of what it should be, right? That's what it should be. Where did I put the? There it is. So with that being said, right, Oh, this is one of them that doesn't say which one's greater than which, right? Which one's greater than which, but we needed to say that the function itself was greater than 0, which this person did. The derivative is equal to 0, and the second derivative is also equal to 0. So it looks like the person who was working on this one messed up on the second derivative. And that's like I said, it's something that's a common mistake we got to be able to pay attention with. How do I know that the second derivative is supposed to equal to 0? It's because they tell us that it is a point of inflection, right? Remember, point of inflection means that it's not concave up or concave down. It is just 0 for the second derivative at that point. All right, so finish that up, guys. Hopefully, you guys will have that completed. And then today, let's see here. Oh man, I wanted to work on this, but at the same time, I feel like we should be practicing this a little bit more. So let's do this here. I got a Desmos activity for you guys. I'm gonna give you guys a link to it. And I'm going to anonymize this, and I'm going to get the student link for you guys. So you guys, if you're already in my Desmos class, you can just go to Desmos and open up this activity. It should be good to go. But if you don't have that, you don't remember your login, it should be your school login or how to get to it. I'm going to give you the link right here. And we're going to be doing this Desmos activity together. Okay, so let's go ahead and take a look at this Desmos activity. Oh. So we got 2 people who've clicked in already. All right, 2 people who clicked in, 4 people who clicked in. You guys get a couple more in there. Let me see you guys get in there. I put the link into the chat. I know I'm making you open up a bunch of stuff, but it's a little much. I know, but something for you guys to practice. By the way, all these anonymous names or these names that they generate for you, they're all real mathematicians, by the way. If you guys ever Google them, you can figure out what they've accomplished and what they've contributed to the math world. Like, for example, if we look at Ada Lovelace, I don't think that's how you pronounce her name, right? Ada was a mathematician, if you Google her name. Augusta Ada King, Countess of Lovelace, was an English mathematician and writer, chiefly known for her works on Charles Babbage's proposed mechanical general purpose computer. Born in 1815, died in 1852. Known for mathematics and computing. World of math has been around for a long time. That's cool, though. She actually had a title called Countess. Anyways, let's see. How many of you guys have gotten in here? We got 18 of you guys who've clicked into this. Only 18? Come on now. Come on. Only 18. There's clearly 33 of you guys. 33 of you guys. This is definitely one that's more fun if everybody clicks into it, because you guys are going to have to create some functions here. So can you guys please click on there? Please. So I can see. And then let's take a look at this problem, okay? So you have 3 functions here that are related to each other, right? The original function, the first derivative, and the second derivative. Our job is to figure out which is which. So you see the little dot right here? Don't click on the box. The box does nothing. But if you click on the little dot right here, you can move it to say which function is which one is the original function, which one is the derivative, by moving the dot and putting it on top of the said function. So it gets a little hard if you're too close here. So pick a point around here. So one of these is going to be the original function. One of these is the derivative of the function, and one of these is the second derivative of the function. So knowing what you know now, right, we should be able to mark which one is the original function, which one is the derivative, and which one is the second derivative, right? And we should be able to back it up with some explanation, right? So we should be able to look at these guys and see which is which. Now, my technique I always look for is usually I look for critical points. right? So for example, right here at x equals 0, I have a critical point here on this graph. I also have a critical point here on this graph, right? Now, which one is going to be which? Well, I already think that this one right here is probably not going to be the original function, right? This one right here is probably not the original function, right? Because, well, it's the value right there is 0, meaning that it's probably a derivative of either this one or that one. Okay, that's what's telling me right there. Okay, well, I mean, it could be possible, but we don't know for sure. Looking at some other critical points, you'll say, knock me. How about this one right here, though? This looks like this one could be the derivative of that one. And I'll say, yeah, you're right. Say, oh, and then, yeah, there's so many points over there, right? How can you figure out which one's which? And we just have to kind of take it piece by piece and slowly as we go. Because right here at x equals to 3, you guys, or 3 point something, you guys agree, right? That looks like this should be the derivative of that. Because there's 0 here, and then these look like critical points right there. So that's a tough one, isn't it? That's going to be a tough one. So I'm going to leave you guys to it. See what you guys think. And then when you figure it out, once you move them over on top of each of these guys and you've highlighted all 3 graphs a certain way, there's a check button that comes up and you can check your answers. Okay? And it will let you know. So let you guys try that out. And then once you guys try that out, I'm going to go ahead and open up the next one. And once you have tried this out, oops, I don't want to share your answers there. You can see which one is right, which one's wrong, and you can share your answers, okay? So we're at 23 people who've clicked in. 23. Thank you, 23 of you guys who have attempted. Once you've finished this and you've done it, you can go ahead and move on to the next part. And let's see how good you guys are at determining which one is the original function, which one is the derivative, and which one is the second derivative. All right. So how would I do this? Well, I said I was going to look at these critical points, but then there's critical points here, and then I don't know which one's which. So maybe concavity would be my next thing to look at, wouldn't it? See, this guy, if I think this is the original function, right, then the second derivative would be all negative on those intervals where it's concave down, which this one looks like it. Whereas if I thought this was the original function, right, which looks like the derivative would be here, it's concave down, and it's neither of these would be second derivatives of it, right? Because these guys are positive values right here. So this can't be the original function because neither of these would be second derivatives. So that's helping right there. I know that this right here is probably not the original function because I don't have any negative values for this concave down part right there. Okay. And then if I'm looking at this function to be the original function, this one down here, right, this one is a possibility because it is a possibility. I have here the original function has a critical point right there, and it's concave up clearly, and these are positive values up here, so it could be the case right there. This could be the second derivative of this, but then when I come over here, well, it's possible. No, it's possible as well. It's concave down right there. It's possible. There is a possibility that this could be the original function and this could be the second derivative. But then that means that this big one right here would be the first derivative, which doesn't work out. Right? If I'm saying that this little one was the original function, and I'm saying that this one is a possible second derivative, I can tell that this one right here is not going to be the first derivative of that one because right here, the function is decreasing, right? This purple line is decreasing from here to here, and this derivative is positive. So that's not possible. That's not possible. That is not possible. So that is not the case, right? So that's kind of like the thought process that you have to go through. And this can be very, very daunting if you've never, done this before. And it's something that you got to practice, and it's something that you got to be able to do. So I'm saying, right, that this guy is the original function. Now, you guys can be able to figure out what is the first and what is the second. So can you guys go ahead and let's see here. How many of you guys have tested it? How many of you guys have gotten it right? Let's take a look here. I decide how to label these functions by first looking at the critical points. Good. That's a great way to start. The function that I marked orange is equal to 0 at all the critical points of the original function. Then I look at the concavity. Yeah, those are the things that you really want to look at. Critical points, concavity. And whether or not you got it right, I love your explanation. So whoever is Augustine, very good explanation, right? Carl, whoever you are, at the maximum, the first derivative would have to be equal to 0. That is very good. Yeah, that's good. Therefore, the last function is the second derivative. Oh, I got you. So I can't actually tell which one is the first function or the last function in your explanation, but I understand where you're trying to go at. Took me 8 tries. I don't know. Okay, that's okay. That's okay. This is, like I said, it's a little daunting, and we'll keep practicing. Once you finish this, by the way, guys, you guys can go ahead and move on to the second challenge, where you get to create your own function, and it will graph the first and second derivative for you. And then you can submit that so that other people can try to see which one is the original function, which one is the first derivative, and which one is the second derivative. So you can try that after you've done this first part. So I'm gonna go ahead and review the answer for you guys for this first part right here. This one right here with the highest point, this is gonna be your original function. I'm gonna say it right now. This is going to be your original function. How do I know? I don't actually know, like just by saying that claim. I'm just, why am I saying it so confidently? Well, we went through the thought process earlier, right? Of what were the possible combinations. And I'm saying that this one has to be it, because if it was this one, right? Then the only possible derivative would be either this one or this one. And it has to be, if I'm looking at it, it has to be this one, because that's the only one that has a critical point right there. You see that? This right here has a relative minimum here. That means the critical point is equal to 0 at that point. That's the only way that can work. But it doesn't work for any of the other points. You see here? The interval from 0 to this dot I have drawn right here is increasing, meaning my derivative should be positive. And my orange line is clearly not positive from here to here. And you'll say, how can you tell it's positive? A function value is positive when it's above the x-axis. So this purple line is increasing from 0 to 5. The orange line is negative from 0 to 5, which means that the derivative is negative, which means that the original function should be decreasing. So that can't work. And I can't put it here as the derivative, because the critical point down here needs the derivative equal to 0. And the derivative, if I put it here, it's going to be equal to positive 6, which is not the case. So that cannot be the function. So I'm going to move that off from there. The other one we're going to try then is this one right here. If this one's the function, which one would be the derivative? Again, look at the critical points, and there are matching critical points here. It could be this one or this one. Both of those critical points look good, don't they? This one or this one, because they happen to have a 0 here at that critical point, a 0 here at that critical point, and a 0 here at this critical point, right here. Wait, no, that's not a critical point. Critical point's over here, right here at -10. But again, here's my issues. From -10 all the way up to -3, the function is increasing, meaning the derivative should be positive. And it's clearly not positive there. It's clearly not positive. So that right there is not the derivative of that. But this one does look like it could be the derivative of that. I'm sorry, that's wrong. This one does look like it could be the derivative of that, because not only does it have the critical point here, but it also has the increasing values from -10 to -3. The orange line is above the x-axis, which means that it's positive, and it follows suit that the purple line is increasing. And then here, right, from -3 all the way to +3, it's decreasing, and we have it down there. So this is clearly the derivative of that. So this is not bad. This purple line, right, and this orange line is the derivative of that. But that leaves us with the second derivative, and this second derivative does not match with that one, because that's what we did earlier, right? This cannot be the derivative of that line. So we were almost correct. This one is the derivative of that line. So we're going to just move that around a little bit here. So if this one was the first derivative, I can say that the smaller one was the second derivative, based off of the information that we just saw, that it's increasing on these intervals and it's decreasing in the critical points, which leaves us that the original function should be this one right here. And we'll go ahead and check it. And it's correct, right? And don't worry, again, if it takes you 8 tries, it takes you 8 tries. It's something that's a little weird, but that's kind of the thought process you have to go through. You kind of like see like, well, can this one be the derivative of that one? Yeah, it can. Oh, it can't, right? And those are the only really options. And if you can see one is the derivative of the other, you keep that in your mind. We don't know if that's the first and the original function in the first derivative, or if it's the first derivative in the second derivative. but we do know that one is the derivative of the other, right? And then we just have to see, is the third function the derivative of the last one we just found, or was it the original function where this one was the derivative of that one? Sorry, I'm saying a lot of words. But yeah, that's the idea that you want to go through for that process. So go ahead and try that, wrap that up and see what you got. I already pretty much gave you guys the answer, so you guys should be able to get that one done. And then let's go ahead and move on to the next one. And this is where you guys get to submit your own function. You get to submit your own function. So I'm going to go ahead and make my challenge here. And you could type in whatever function you want. Now, some of you guys are like, I don't know what the function should be. You could do a quadratic, but if you do a quadratic, it's very, very easy to tell, right, where is the original function, right? So for example, if I just did x squared, right, and I asked it to graph it, here's what it would look like. Right, that's not too bad. You can also change it though. Let's go with something complicated. You can just go with factors. You don't have to have it like in general form, right? You can have it in factored form. So I can have something like, instead of x squared, I can have something like x minus 2, right? And then let's go with x plus 5, right? And then we can go with, I don't know, let's go with, let's make it a cubic. Let's go with x plus 3. Let's go with that, you know? And let's have this graph it. Oh, right? And then we can also add some fractions in there or make it decimals in there. You don't have to have pretty numbers. You can have it look like this. And then you can see like which one's which, you know? Let's make that even smaller. So I leave it up to you guys, however you guys want. You could also add trig functions if you want. If you want to try it out, have it graph all these different guys for you. And then once you do that, it's going to ask you, are you able to tell which one's the original function and which one's the derivative and which one's the second derivative? Right? So looking at this guy, I should be able to tell which one is which before I submit. So looking at this, right? This straight line is probably not my original function because the other ones would be, the derivative of a straight line would be a flat line, a flat horizontal line going across. And I don't have that here. So that's probably not the function. It could be this one right here. And it could be this one right here that has this curve, right? So I'm looking at this one right here with this curve. I have a critical point right down here, which matches that that 0 right there. So, and it's decreasing from here, so it has negative values, which is on that line right there. So this is clearly the derivative of that, right? Because it's negative values all over here, all the way up to right there. And then it's positive values over here, all the way up to right there. But this is the derivative of that, but this is clearly not the second derivative, right? Because we just talked about this. That orange line, its derivative would be a flat horizontal line. So this green line is not the second derivative, right? So we just have to move them down a batch. So this is actually the first derivative, and this one is actually the original function, and then that's actually the second derivative. And we just go ahead and check that. And it's correct, right? So you have to describe how you labeled them, right? Explain what the function is doing. I'm sorry, explain what the derivative is doing, and explain what the second derivative is doing compared to the first derivative here. And then once you submit that, you can submit the challenge, and then everybody can take a look here. So that's my challenge right there. One other person has done one. Some of you guys are still working on yours right now. So can you guys go ahead and finish that up? I want to see some of your stuff here. So this one is beautifully. Let's take a look at this person's example right here. You're the creator. You tried it. Let me try it. Oh wait, this just shows. Whoops. I click over here? I do click over here. So if I click over here and I click on it, then I can try it myself. So I can go over here and move it. So if you guys can you guys try submitting your stuff so we can all have some of these to try to see which one's the original function, which one is the derivative, which one's the second derivative, to test that out. Right. So for this person, I'm pretty sure that's the original function. That's the first derivative, and then I'm pretty sure that's going to be the second derivative. Right? Because I have a critical point right down here. Right? I have it decreasing here, so it's negative values. That's why I know the orange line is the derivative of that purple line and not the green line. Because like I said, if I'm drawing this out, I can see that it's decreasing from here to here all the way down to almost 0. So right here, it has a negative value all the way up to there. That's why it's not that green line. Okay. So let's see. How many more other people we got? Do you have any other submissions? You guys are still working on it? Okay, you guys are still typing in functions. Try it out, guys. Try, like I said, you could try cubics, quartics. You don't have to make it look perfect, right? You can go with sine functions, right? Cosine functions. Do whatever you want. Plug it in there. Let's take a look. I want to see you guys try it out. And then once you figured it out, I want you guys to try to answer someone else's response. So get in there. Get in there and do it. Hurt my back yesterday, and now I can't bend down to get my own water. Such a shame. Like I said, once you finish yours, try someone else's. See if you can figure out which one is their original function, which one is their first derivative, which one is their second derivative. Which one is which? Which one is which? And then with that, let me double check attendance real quick to see who is here. I'm just missing 2 people. Okay. All right. Oh, we got 3. We got 3 submissions so far. So try some other ones, guys. Try some of the other students. Those of you guys are done. Try each other's. And then those of you still working. Let me see. What you guys got? What do you guys got? Oh my God. That's gonna be a tough one. I don't know. Are you able to do that yourself? That's gonna be a tough one. Augustine, whoever's Augustine Cauchy. Who got Albert Einstein? Oh, it actually shows names if I hover over them. Whoops. Albert Einstein, what you got? Ooh. Oh, hurry up and get that submitted. I want to see people, how many people can get that one right. Augustine's like, screw it, I'm throwing that one in there. What else we got? That's not bad. It looks skinny, but that's not bad. Like, people should be able to tell which one's which off that one. You know? That's not bad. Oh my God. I don't even think you'll be able to move the dot onto the right one for that one. What is that monstrosity? That is a trig function combined with it looks like it has a quadratic inside the tangent function, and then they're adding a cubic outside of it. If you put parentheses around that, that'll include it inside the tangent. If you put it outside like that, that just becomes, well, that. Oof, that is crazy. Oh, good, more submissions. All right, guys, there's like 6 of them up here. Can you guys go in there? I feel like I get a free coupon. What else we got here? Oh, nothing yet on this one. Okay. How about you? Ah, good. Let's go. Ooh, actually, though, that one's interesting to me because there's stuff off screen. I don't know. This must be this one. Ooh, that's a good one because it looks tricky. But then you realize, like, oh, there should be a flat line at some point. Not bad, Fibonacci. Not bad. I like the cosine with the function inside the cosine. Good. How about you? Ah, got a crazy looking cubic there. Good. That one's going to be a tough one because you can't see it all. But not bad. Same thing, not bad. Good cubic. Let's get that in there. Go ahead and get that submitted so then everybody can give that a try. And my gosh, look at that one. That one is a 5th degree polynomial right there. That's a 5th degree polynomial right there. How about you? This one's I like that function. It should be able to graph it. Oh God. That one, like, the lines are so thick right there, it made it black. I'm sorry, I don't know if you were still typing it. Whoever this was, I just needed to see what that graph looked like. I still took a look there. All right. So yeah, go ahead and try a couple of these, right? Try to see if you can answer them. Not just yours, right? Try to see if you can answer some other ones to see which one is which. I want to see by the end of the day, you guys should have like more than just a couple just one or two check marks on here. I just want to see everybody go in there and give it a shot, give it a try. And then, yeah, that's it right there. And then, man, I took too long on this one. So we're going to be, like I said, this is how it's going to start off. And we're going to look at analyzing the graphs and seeing which one's the derivatives of which, right? And that's going to lead us to our next part. I'm going to wrap it up right here, guys. I'm going to give you guys the title of the next thing. We didn't actually have enough time to get to it, but this is what I want to get to right here, right? Basically, what I want to get to is, hold on a second here. Where am I? Over here. Is this zoomed in enough? There we go. All right. What I wanted to get to, which I didn't get a chance to get to. That's right there. So let's go down right here. This is what I wanted to do, and we're going to title it, and then we're going to end up right here, is basically sketching graphs of function. Right? And their derivatives. All right, we'll do this next time. With that, though, let's just call it there. Hopefully this wasn't too bad. And again, if you're confused, don't fret too much. The graphing part is always a little bit more difficult than the analytical part. Like us taking derivatives and set equal to 0 is a little bit easier to do than applying it graphically. But well, hopefully I'm going to make you feel less uncomfortable with it and a little bit more confident with it. Okay, so we'll keep practicing this. Don't worry about this too much. We'll come back on Thursday and try this out. I'm thinking I got to give you guys a quiz at some point because the grades are going to be due soon. So I'm thinking we might have a quiz on Thursday, but it won't be doing it graphically. It will be doing it analytically. So I might ask you like, hey, here's a function. Find the critical points for me. Find the second derivative for me. Find the point of inflection for me. So be ready for that. So if you haven't done the homework already, get started on the homework that we have assigned, right? And other than that, guys, that's it for me today. Have a good rest of your day. We'll start on these notes later. And then come in ready for a quiz on Thursday, okay? The quiz on Thursday is going to be one that is going to be turned in and graded. So be ready for that. All right, guys. Have a good rest of your day. I'll see you guys later. I have office hours today from 1 to 2. All right? I'll see you guys. So long. Farewell. Bye-bye. See ya.